On our very first episode, we coded up something called as Conways game of life, where we saw that very simple rules, when you code it up, can give rise to very complex behavior. I'll put a card to our first episode right about here. All right. This week we wanted to take it up a little bit further and code up a particle system that can interact with each other. So let's get going. Hey,
RK.
yeah, I mean, too bad we lost our keyboard, man. I mean, the keyboard doesn't work.
The TV is
so we'll have to sort of work with a new keyboard. If you're used to the clickety-clack of the TVS mechanical keyboard, you're going to miss it this week. So until we get back, a mechanical keyboard, you'll have to like sort of get used to this one. This one doesn't have the clickety-clack, but I'm hoping I can fill up those gaps with my. You'll have to make do with my voice this episode.
Nice.
All right. So what are we going to do today? What I thought we'll do today is we'll extend our game of life
using particles.
Using particles and simple interactions or simple rules of interactions with each other, but they will sort of give rise to complex behaviors that you cannot foresee, that you have not essentially programmed them into. Now let me just switch cameras over here. All right. So that out of the way, this is what our inspiration was for this week's episode. All right. So we'll put a link to this video in our description, and we'll go from there. All right. So when you talk about Conway's game of life, just as a refresher, let me just bring up our own site. I should probably set it up as the homepage, man, so that as soon as you open it. So if you go back to our first episode, there's like this very beautiful Conway's game of life. We somehow made it psychedelic, whereas most implementations are not actually
multicolors.
Are this colorful. So anyways, so this is Conway's game of life, where very simple rules like overcrowding and undercrowding gives rise to this very complex behavior. So we'll take it a step further, like I said, and we'll make it a little bit interesting. Okay. So what are we going to do today? We'll call it Game of Life 2, which will be the title of this episode. And we'll design a very simple particle system, which has different particle types. Each particle type will have its own color and things like that. All right. Each particle type defines its own interaction with another type. All right. So, for example, how a red interacts with, let's say, a blue, a green, or a yellow, or a purple is all defined. Is all either randomly defined, or we can like sort of define them however we want.
Right.
Okay.
Right.
Each interaction distance between each types is unique. So a red might interact with a blue
only when the distance is
only
less.
when the distance is less, or only when a distance is a specific threshold.
Got
all right. So over here, what I'm trying to say over here is that I think the green ones over here are attractions, and the white ones over here are repulsions. So they can either get repelled or they can either get attracted. All right. In the case of our game of life, the force of interaction is modeled after a very simplified version of gravity. All right. So the gravity equation, we'll just look at it in the next slide. And and just so that these particles don't collide with each other, they all have attraction or repulsion. But there's always a chance that they could like sort of, if we don't handle them carefully, these particles could like sort of enter each other, right? And just so that doesn't happen, particles will always repel each other when they get too close to avoid collision. This is so that they can avoid collision. With that being said, let's just look at the gravity formula. All right. So the force between two particles or two planets in the case of gravity is G, which is a constant, multiplied by the mass into mass of first one and the mass of second, divided by r square, which is the distance between the two bodies, right? Or the distance squared between the two bodies. And our simplified version will simply say that force is equal to 10, which is a number that we have chosen arbitrarily, divided by r square. R square will be the distance between the two squares. So, yes, for all intents and purposes, we are excluding M1 and M2 because we don't have, our particles as such do not have mass. All right. That being said, let's just look at what we have for setup. All right. So, as per usual, we have a
canvas.
I've pre-included all of the requisite code that we are going to use. I mean, all of the JS file skeletons I have like formed. I mean, I have a so we are going to be working with a lot of constants in our code this week. So I have a file here called commons.js. So instead of putting all of our constants at the very beginning of our JS file, I have like put them in a separate file. So we'll just go through them. What are the constants we're using? So all of the types we have defined. This is a lot like enumerations in Java. So I've basically used the same concept to define types, where I have numbers assigned to each color. I've also defined the colors beforehand. I also have an enumeration over here called interaction, which is either attract or repel. And there is also a couple of variables that we'll be using. So I have like a minimum interaction distance and a maximum interaction distance. I'm not sure where we'll use the minimum interaction distance, but maximum interaction distance, I'll show you where we'll use it. All right. I've defined the size of the particle. This will be basically the radius of the particle. And I've also defined a particle diameter. Basically pre-calculating this r square, right? I mean, this not r square, but we will basically require them to do collision detection. Right. So I'm like, particle diameter is equal to r into 2. And the number of particles that we are going to do. All particles within this system. So, going back to this slide over here, if we allow these forces to act against each other, you will very soon find out that they will have for example, what can happen is that red might be attracted to purple, but purple might be repelled by red. So what will end up happening is that these two particles will sort of chase each other, and they will have no maximum speed as to how much they'll chase each other. So all particles will have to abide by the maximum speed of this universe, which is 1.5. All particles will also have to abide by this viscosity. All right. So if viscosity is 1, it means they're like free flowing, basically going through air or in space. But viscosity will say 0.9, which is, let's say they're like moving in a very sort of viscous liquid. All right. So each time there is some velocity, we'll remove away some aspect of the velocity from their speed. I've also defined a class called as the particle. All right, which has it has a constructor, and this particle can be of a random type. So I have this dot type is equal to so for now we'll begin with one of 3 types, and those 3 types would be like red, green, or blue. Okay. So we'll start with those. So it can be one of these 3 types, and then we'll also define something called as an interaction list that we will work on. What those interaction types is later. And they can be, they also have a location. Their location is randomly determined, on a certain place on the canvas. And they will also have a velocity, which to begin with is 0 because they have no velocity. I have a function called add force. Force adds to the velocity, and then ultimately in the update function, the velocity is added to the location, and then they are rendered on the screen. So as our first, so to begin coding, let's just write out the render method. All right, and to do this, we'll have to so each particle can be of many types, right? So we can say maybe if this dot type is equal to types dot red. So if it is if it is red, then say context dot fill style is equal to, I already have the colors defined, and I can just say colors dot red, right? So I can just go about them doing this. So I have to do this 5 times. So I'll say else. Boy, I missed the clickety clack, man.
Yeah, I also. Me too. Me too.
Okay, so I have green, then I have blue. So I have blue, and then I have yellow, and then what was that, purple? Yes, purple. So there you go. So I have basically done this one. Let's say context dot begin path, context dot arc, and arc will have this dot location, dot x comma this dot location dot y. Radius would be the particle radius, right? Which we have defined here as particle size. So that would be the radius, followed by 0, and the end angle would be I forget. I mean, I think
pi.
it's it's 2 pi, but we've already pre-calculated 2 pi, and we have put it as a constant on one of our on CodeSpace API. And the reason we pre-calculate this is because and this can be true, right? Now the reason why I'm pre-calculating this is because remember, if you look at the number of particles, the maximum particles is 600. You'll have to 2 into maths.py, you'll have to calculate it 600 times. That's why we sort of pre-calculate it, and we keep it. So yes, so that's just about drawing the particles on the screen. Let's just look at our main file itself, which has an init. I mean, it has a start animation. It creates all of these 600 particles. When you create a new particle, it can be of any type. And then I have an enum loop that just basically calls the update first, and then it sort of renders it on the screen, and then calls the request animation frame. Now, if we were to execute this, let's see what this looks like. All right, so nothing happens for some reason. Okay, so the one thing we forgot was the context.fill, which was ctx.fill, and I think that should sort of render all of the particles on the screen. So there you go. Yeah. So that's all of the particles on the screen, and obviously nothing happens between them right now because we've not defined any interaction as such. Right. All right, so I'll have to sort of first define the particle interactions and how they interact with each other. Right. And to do that, I can say, so this is already an array, and I can say particle interactions of types.red. So over here, we are defining how red interacts with other particles.
Correct.
So I can say is equal to, which is an associative array, sort of an associative array. So I can say 1, which is red. How does it interact with itself? And I can say types.red. I mean, it interacts with red by, so I can say type is types.red, which means, okay, so just ignore this 1 over here because we definitely need that to sort of define an associative array. But over here, we define that it interacts with red by what? So I can say interaction is equal to interactions dot so I can say that red particles will always attract, so I do believe it's called interactions. Oh no, it's just called interaction. So I can just say this is interaction dot attract, and by what distance does it I can just say 20. All right, and so on and so forth for all of the other colors as well. So this interacts with, let's say, green by repel at a distance of 30. So I'm just going to define it like this. I'll remove this part, and then it interacts with, what we should do? We should forward through the entire thing. So this is interaction. Oh, I should say distance. Okay, distance. And once again, it attracts blue at a distance of 20. All right. So I have just defined what red interacts with. I'll do the same thing for, let's say, green and for blue as well. All right. So we are just basically defining all the interaction type. Green interacts with red by, let's say, attracting it at a distance of 20. I'll just leave it like this. Green will repel green at a distance of, let's say, 20, and it will attract blue at a distance of 30. Once again, this is all just arbitrarily defined. Nothing is, sort of nothing is thought over and everything. I have blue, which will attract, let's say, okay, so everybody likes red. It will repel green at, let's say, 20, and it will attract blue at, let's say, 30. All right. Completely arbitrarily, I've like defined all of these. So now I have the particle interactions. Okay. Let's just go to the particle. Now the interaction list over here, I will have to say, okay, so where do I get the interaction list from? I will just say that this interaction list, get it from one of these particle interactions from. So whatever your type is, so I can just say particle interactions of this dot type. Okay, so let's just understand what happens over here. So so this particle has an interaction list with other particles.
Right.
The interaction list is, let's say if this is red, for example, so particle interactions of red will give me, where is that again? So it will give me this associative array. So it will know how it needs to interact with each other.
Yeah.
All right. That being said, let's just go to the update function over here, where we will start to define our interactions with other particles. Okay. The first thing that we'll have to do is find out if this particle is within a certain distance of another particle. All right. So going back over here, if let's say this red, we we focus only on this red, for example, we'll have to find out it needs to interact with other particles. Very obviously, we cannot have it interact with we cannot check it against all of the particles, because that would be like 600 into 600 maths that we'll have to do, because each particle interacts with itself. So we cannot obviously code that. So we will say that if the distance between, we'll just say take this particle, find out all of the particles that exists within the maximum interaction distance that we have already defined. So if you look at our commons, we have said that the maximum interaction distance is 30. So any particle within that distance, we will take that and we will define interaction only for that. Okay, let's do that. Where is that? Okay. All right. So to do that, what I'll say is that let's open a for loop, which will just basically go through all of the particles. I'll say for let I is equal to 0, I less than particles dot length I plus plus. All right. Particles is like global variable, which will basically contain all of the particles that ever exist. All right. Now, obviously, you don't want this particle. All right. So first, let's get a distance between this particle and the next particle. So I'll say let distance is equal to get distance between. Oh no! You know what? First things first. Let's say if this dot or particles of I is equal to this, then continue. Basically, we don't want this particle to interact with itself. That's one thing. Next thing, we'll say let distance is equal to get distance between this particle and the other particle. This dot location dot y and say particles of I dot location dot x, and the same thing with y as well. All right. So the get distance is an inbuilt function which is there in codespace.api, which will basically return the hypotenuse between the two. Basically that's the distance, right?
Yeah.
And if distance is greater than this max interaction distance, then don't even do anything, just continue with the loop. Don't do any more math. Already this is like a big loop where we are sort of interacting with all of the particles, and so this will sort of give some respite to our to the CPU. Now if distance is let's say all right, so now we have this distance. All I have to do is like sort of loop through this interaction list, because this is where it's all defined, right? I mean, this is where the interaction is defined. So I can say if, no, I'll have to sort of do a for loop. So I'll say for index in this dot interaction list, let interaction is equal to this dot interaction list dot idx. All right, so this will basically give me the interaction, the specific interaction. Okay, so if once again going back over here, so if this particle is of type red, then it will just basically give me this, and it will tell me what sort of interaction is going to happen. So now I have that very specific interaction. Okay, so I'll say if the distance is less than interaction dot distance. So remember that each particle works with another particle at a specific distance, and we only have to like sort of do it within that distance. So if the distance is less than the interaction dot distance, only then do the thing, right? So I have the interaction. Before that, I'll have to check if the interaction type is if the type of interaction is the same as this dot type. So I'll say if this dot type is equal to interaction dot type. Only if the types are the same, then check for the distance, and then we can proceed with the. Oh, but it's not this. It's not this dot type. It's particles dot type, right? If particles of I dot type. So basically, we are defining. Right? I mean, we have to say what is the interaction with the other particle type, right? So if the other particle's type is of this, and if the distance is less than this, only then do the interaction. Okay, so if this and if the distance is less than the interaction dot distance, only then calculate the force. How do we calculate the force? We'll say let force is equal to, remember what we said in our slide over here. We just said 10 by r square.
Right.
So we'll just say 10 by distance into distance. That's all. Right. So that's our force. Once we have the force, now remember this force is actually a single dimensional force. We'll have to convert it back into a two-dimensional force and into a two-dimensional force, right? And to do that, we'll take a chapter out of, or we'll take a lesson out of the collisions that we did, and we'll use a little bit of trigonometry to do that. Okay. So first things first, I'm going to define something called as a tangent. Okay. So I'll say let tangent is equal to, and to calculate tangent, I'll just say math dot a tan 2, which is basically the angle between the two existing particles. So I'll just say particle dot x minus particles of I dot location dot x minus this dot location dot x, followed by comma. So the a tan requires an x and y, so which is nothing but a difference between the x positions and the y positions. So I'll just sort of take this and I'll put the y positions as well. So I'll have y and I'll have y. So I have the tangent, and to convert them back into x and y, all I have to say is say let f of x is equal to the force that we have already calculated into math dot sine of the tangent. So I'm basically converting them back to point variables, or to say or in which direction the force is. All right. And y would be math dot cos of tangent. Okay, so I now have the direction in which they travel. Now remember, we have calculated the force and we have everything. Now this is because this is modeled after gravity. This force is almost always attraction. Not almost always, it's always attraction. If remember, it also has to be repelling. Right. All right, and if it is repelling, it's a very simple thing for me. All I have to do is say force. All I have to do is negate force. So I'll say if interaction dot what is that, attraction type, what did we call it? I keep forgetting. Dot interaction. Okay, so we just call it interaction. If interaction dot interaction is equal to interaction dot repel, then I have to say force into equal to -1, which is just basically negating the value. So once I have negated the value, if it is repelling force, they will sort of move away from each other. So now I have the force. and I have done this, and I can just say let force is equal to new point of f of x and fy. I'm saying f of x, no, it's fx and fy. So basically I'm creating a new force point variable, and I can say this dot add force, add this force over here. Or you know what, this is a duplicate variable. I'm just going to call it force point for now. All right. So I'll just say this is the force point. So I'm just adding it. So this adds to the force point, right? The force adds to the velocity, and the velocity will ultimately over here add to the location. We'll change the location. Okay. Now remember, we are adding something to the velocity. And remember, one of our things was that these particles should not have like, ultimate speed. I mean, they should not have like, they cannot be faster and faster because we have defined something called as a max speed.
Right.
So we'll just check for the max speed in the add force itself. Say if this dot velocity dot x is greater than max speed, then we'll just say this dot velocity dot x is equal to max speed. What do you say? Right? I mean, this works. Now remember, it can either be positive or negative. So I also have to check for the negative value, right? I mean, because it could be going in the other direction. If it is less than max speed, then we'll just say velocity dot x is equal to negative max speed. And we'll do the same thing for y as well. All right. So we'll check for the max speed at y as well. All I have to do is like, change all of these values to y. So I have y and I have y. So now I have like the max speeds already defined. All right, perfect. So this works perfect. All right, so I have the update. I am adding to the location, and then there is a velocity. And velocity, I will also have to like, sort of give them. So I'll just say this dot velocity dot x. I'll also have to take care of friction or the viscosity of the fluid that they are flowing through. So I'll just say velocity into is equal to whatever that constant we have defined over here. I'll just say viscosity. So I'll give them like a specific viscosity, and velocity dot y into is equal to viscosity. All right. So they so now they will. So we should see some action happening over here. Let's just see what happens. All right, uncaught reference error IDX is not defined at particle 54. Why do you say that? This is let IDX is equal to this dot interaction list dot IDX. There you go. All right, so you can already see the interaction happening over here, and
wow.
So some interactions is already happening, but you can see that these particles sort of enter each other. I'm not entirely too big of a fan of that happening, right? So you can see the red and green over here. They've like sort of overlap to each other. So remember what we said, I think, on our last point over here. Particles will always repel each other when they get too close to a white collision. So they might. So basically, we'll have to like sort of do this entire exercise again, but only if the distance is sort of less than less than the particle diameter. So let's just do that, right? So we have the interaction list. I mean, we have the distance. Where does this for loop end? It ends over here. I can say if distance is less than, or do I have to calculate distance again after this point? So yes, so it does turn out that I'll have to calculate the distance again. The reason for that is because we've like already defined, I mean, we already have the velocity at this point, right? I mean, we've done this force, we already have the velocity. So at the very next instant itself, they could like sort of overlap into each other. So I'll have to calculate distance again. I'll say distance is equal to, once again, I'll just say distance is equal to get distance, but we are sort of doing something called as a priori collision detection, which is, calculate the collision beforehand itself. Calculate if the collision will happen beforehand itself.
Correct.
So this is sort of a priori. So I can just say plus velocity dot x. So I hope this is clear as to what I'm doing over here. So I'm just pre-calculating if the if it will collide on the next iteration, right? That's what I'm pre-calculating over here. And the same for the particles. I'll just do the same for the particles, right? So I'll just say plus velocity dot x, say plus velocity dot y. That's it. All right. So now if the distance is less than the distance of diameter of the two particles, which is this particle diameter. So I'll just say if it is less than this particle diameter, then you basically do the exact same thing, right? Except this force is always negative. I'll do the exact same thing, right? I'll say force is equal to minus 10 because it's always repelling, right? So I'll just say force is minus 10, do the same thing, this dot add point of force point. All right. And I think this is the only thing that is required to sort of fix that repelling issue. And now let's see what happens. So at 75, cannot read property 23. What? Oh, there you go. That's a missing plus over here. So yeah, so we just add the plus over here. I think that should sort of fix this. So we have the add force also done, and then we have this. So the force adds to the velocity, and once we have done the force, let's also change the location itself over here so that it always appears outside of each other. So we'll just say this dot location dot x is, we'll just do this beforehand itself so that they always sort of go outside of each other.
Yep.
All right. So once we do this, I think we should see something remarkably different.
Oh yeah.
Yeah. Yeah. There you go.
Oh yeah. So the reds and the blues seem to be
very friendly with each other.
Yeah.
Seem to be very friendly with each other. Nobody likes the greens because the greens are. Okay. And this is much more lifelike than other than the Conways game of life, right? I mean, because this sort of defines what do you say? Cell-like behavior, right? I mean, these actually look like cells to me, right? What do we want to tweak? I mean, I think green was a little bit different. Let's just go back to our definition of what we did. So there is green. So attract, repel, attract, repel, attract. 10. I mean, basically, we've defined green and blue as exactly the same.
So everybody, red and all the three are repelling green, right?
Are repelling green. So green also repels green. So let's just change that and change this to attract and see what happens, right?
Yeah. And all the greens will stick together.
All the greens will stick to each other. Yeah. There is, I think, if we take a book or take a lesson from one of our earlier there is a way to actually make this interesting in that we can just make this fill style, let's say 0.2, for example. And we should see some trails and all going through.
Okay.
I mean, I'm going to remove the trails because it sort of distracts. It's a little bit distracting. We can make the trails a little bit smaller by making it 0.3. So the trails should be smaller. But for now, just so that we can witness the interactions a little bit better, we'll just put it back. So there you go. So that's the interactions. That's the interaction model between all of these particles. All right. So so over here, what we've done is we've sort of said that these are all. We have predetermined what the interactions will look like.
Right.
There is a better way to do it. We can just sort of completely randomly say what these interactions will look like. Right? So that each run of this program will define completely random game of life scenarios, right?
Right.
Let's take a look at when blue and look at this. Look at this. When blue and red come together, they become very rowdy, man. They become very, very. And the bigger their mass are, the more rowdier they seem to become. Right? Yeah. So this is just 600 particles, is it?
Right.
Yeah. This is just 600 particles. Yes. So there you go. That's beautiful, right? Let's just improve this. And in that, remember, we've defined many types of particles. I mean, not many types. We have defined 5 types, but we're using only 3 right now. Let's, what we'll do is we'll just comment out this thing. and we'll define this particle list completely randomly. Just do that completely randomly, and let's do that in the start animation. All right. So we have defined the particles over here. Let's define the particles list. Now remember, we need so there is 1, 2, 3, 4, 5. We need 5, and each one of those 5 should have 5 different types of interactions.
Correct.
So we'll need to have 2 loops. So let's just do that, right?
Yeah.
So we'll say for let I is equal to 0. I less than or equal to 5, because we need from 1 to 5.
Yeah.
I plus plus, and we'll say let interaction list is equal to this one. So this is like, this will go and sit in that particle. This will go and sit inside that particle thing. Say for let j is equal to 1. Once again, it's from 1 to 5. J less than or equal to 5, j plus plus. We're not starting this from 0, so please keep that in mind. We'll say the type is equal to j. So when I say, okay, so we'll just define a variable here. I'll say let type is equal to j. So this type would be from 1 to 5, or it would be from, red, green, blue, yellow, purple. So it'll be like 1 to 5. Okay, so we'll say let random number is equal to parse int of a random between let's say 0 and 100. I'm just taking a random number. Basically, I want to define the interaction type, and I want to define the interaction type randomly. Okay, so I'll say if I'll say let interaction type is equal to interaction dot attract. By default, it's attract if random number modulo 2 is equal to 0, which means every even thing we'll say interaction type is repel. So they'll either be repelling or they will be they will be this thing.
Attracting.
So I have the interaction type defined. I also need a distance. So I'm defining 3 things over here: the type, the interaction, and then the distance.
Correct.
Now distance can only be I don't want the distance to be a random value between 10 and 30. I am saying it can only be 10, 20 and 30. That's it. That's all I want. So I'll define a random variable for that. Say I already have a random number, and is equal to parse int of random between, I'll say random between 1 and 4, right? Because I want it to be between 1 and 3, this random between will not return 4 itself. It will only return 1 and 3. But just so that, we don't have an issue where it becomes 4, I'll say if random number is greater than 4, then just make it 3, or else let it just, random number. All right. And I will say let distance is equal to random number into 10. So it'll either be 10, 20 or 30. That's the distance. So now I have all of the 3 variables. I'll say let I'll just say some VV is equal to type is equal to the type, interaction is equal to interaction type. You get what I'm doing over here, right? So basically I am forming this, as a variable over here, right? And I'll say distance. Distance is distance. So I have all of these 3 things defined, and I can say that this interaction list of j is equal to VV. So I have this one. And finally, this particle interaction of I is equal to this entire interaction list. All right. It's a little bit difficult to follow what's happening over here, but ultimately this particle interaction at the end will look something like this internally, where it is an array of arrays.
Got it.
All right. That's what. So this is completely randomly defined over here. And also let's just go back to our particle where we have defined only 3 types. Let's just say this is a random number between 1 and 6, and if it is greater than 5, just make it 5 so that it takes up all of the 5 variable types. I think that's about it. That's our, there you go. There you go. So every run of this program, we should see completely random game of life play out. Right? So let's just take a moment to see what we are seeing over here, right?
Yeah, looks like the purples and the reds are sticking together.
There's the purples, yellows and reds are sticking together. The blue seems to like green, but green doesn't seem to like...
Right.
Doesn't seem to like this thing.
Yeah. And the greens are sticking together also. Yeah.
All right, I'm going to go for another run.
Right.
Let's see now what happens.
Yeah. Oh, now the purples are all nicely sticking together with blues, with a few blue.
Look at the yellows over here. They sort of behave when they are in very small numbers. Hey, you know what we've forgotten to handle?
The walls.
We forgot to handle the walls. Let's just go back. Where is that? So we have the update. We also have the distance and the location we've added. We'll have to say if location.x is greater than the width of the screen with minus particle size, right? I mean, or I have to say this dot, or if this dot location dot y is less than particle size, right? I mean, if they go either on the right hand side of the screen or the left hand side of the screen, then say this dot velocity dot x into is equal to -1. All right, and we also have to make sure that if they are really gone outside of the screen, we just reset them back to wherever they were, right? So we'll say if is greater than this, is this one, then just say this dot location dot x is equal to width minus particle size. Is this correct? Yeah. And the other way around also, where if this dot location dot x is sort of, what is this y and x? I mean, it should be x.
Correct.
Is that what you were looking at me for? Yeah. Call me out, man. No, I mean, I'm not an expert coder or anything.
No,
you can just call me.
Mistakes.
I was going to tell you. I mean, sometimes, I know, I understand. Sometimes there's a flow and you don't want to interrupt the flow. Yeah, but I think that's fine. So if it is less than particle size, then just make sure that it is sort of, if this doesn't happen, right, they will, if you don't handle this, they will somehow creep to the to outside the screen. I have observed that. So this needs to be put.
Correct.
We'll do the same thing with y. Let's just be a little bit careful. And if it is greater than the height minus particle size, this dot location dot y is less than the particle size. I mean, when I say particle size, it means basically of this. We are also considering the size of the particle.
Yes.
Dot velocity dot this thing is into equal to -1. If this dot location dot y is greater than height minus particle size, then y is greater than height minus particle size. Location dot y is less than particles, and then y is equal to particle size. I think this should take care of the wall collision itself. Let me just say wall collision. There you go. So now they should like sort of just bounce off the walls. And I think we are like sort of done. So this is once again a random play. There you go. Trains. These trains start to form for no reason at all. And there you go. They like completely bounce off the walls and they're going. So trains start to form between, because of the interactions. Let's see who ruins this.
And there are some clusters there.
There you go. Some clusters that happen over here. All right. What else can you see?
And sometimes these
look at this
get
long
broken
trains.
up. Long trains happen.
Yeah.
Sometimes they get broken up.
Yeah.
Very nice.
Maybe we can reduce the viscosity so that they're a little bit more free flowing.
Okay.
And see how what happens, right?
Yeah.
So that can be easily adjusted by just going to this commons and say.
Where have we used the
0.98.
viscosity?
I have, right? I mean,
Okay.
so in the particles, I'm just saying.
There.
Yeah,
Okay, got it.
right. So so they lose a little bit of energy each time. I've reduced the viscosity now, but the problem with this reducing of viscosity, what happens is they have too much force. They don't have enough time to sort of interact with each other, and they sort of always fly away from each other. So maybe instead of 0.99,
it's like new generation, they break up faster.
Yeah, they break. Nice reference over there. So I'll just say 0.91.
Okay.
Just a little bit less. Yeah. So increasing the viscosity sort of gives them the chance to interact with each other.
Right. Very nice.
More.
Very interesting.
Yeah.
So in this, the greens and the blues are sticking together.
Yeah.
This run.
The yellows are completely inert.
Yeah.
Right? For some reason.
Gotten into clusters and they've become inert.
Yeah. The blues and the greens are the only ones that are like super active.
Blues and greens are active.
Are the ones that are active. Yeah, each
run is different.
like different. Yeah. So there you go. In this one, the yellows are very active. Yeah. So it just might be that they all sort of. You know what? What we've done is over here. Remember the interaction. They're either attraction or repulsion. Right? So we can say we can like increase their.
Repel will be less.
Repel will be like a lot lesser in the population.
Okay.
They'll all like sort of attract each other.
Okay.
So we can. So I can say 3, right?
Yeah.
Only maybe every third of them is like repelling each other, so that there is more interaction between them.
Yeah.
If you do that, yes, so you will see more interaction between them happening. Let's just go break for it and say every 5. I'm just going to say 5, so that the repulsion is very less.
See, we are doing this for 6. If it is I equal to 0.
No, but I'm saying I less. I should say 1.
No. That is you're doing it in this one. That is fine.
No. This also should be 1. This also should be 1.
Okay,
got
it.
That was a mistake.
Okay,
that was a mistake.
Okay, let's.
All right.
Ooh, this is much more like bonding seems to be happening.
Much more bonding. Yeah, because we've done 5, right?
Yeah.
Much more bonding. They form much more. So So I'm guessing. So I'm guessing there is a much more intelligent. Oh, there you go, man. Yellows and blues. One of them attracts and one of them repels. So they form this weird. Look at this.
Yeah.
Look at this. Green and yellow have some sort of special connection.
Yeah.
Yellows by themselves are like very calm, but when they have a green involved, they become very rowdy, or they become, something happens to them.
Sure.
It's great. Greens and blues are the ones that are most active.
Right.
Oh man, look at this. Yeah. So a proper particle system. This looks more alive.
Yeah.
More, what do you say?
Very interesting. Unless other particles come around it, the particles get sort of frozen. But when somebody comes, then they can become part of it and move around.
And you'll have to agree, this is much more interesting than just Conway's game of life, right? I mean, you can see all of the different interactions they have. This is a lot more colorful as well. Right? Yeah. You want to refresh once again, see a new interaction? All right, let's do that.
Yeah.
So I think one thing we can say over here is that this is not true physics, right? I mean, but you can very clearly see the beginnings of molecules and atoms, and probably in a primordial soup on an ancient Earth. This is what it would have looked like,
right?
Where certain amino acids and everything just came together. This is probably what the interaction would have looked like. Possible. And you can very spontaneously see single-celled life and multicellular life, and just see multicellular life come arise together. All by itself.
Yes.
This sort of makes me.
Can we do? That will be so something complex would be to see that the more particles that have come together, somehow we increase their stability. In the sense,
stability. Oh, right.
If they've already come together, then it is difficult to break them
apart.
Wow, I don't know how, but that will be very difficult to code.
I mean, we can. What we can do is do something like where is that particle.js? We already have this distance, right?
Right.
Or we can say if within take a particle, see how many particles are there within a specific radius. If there are more of them, we can like reduce the intensity of the force. Right? This 10 over here we have chosen randomly. I mean, we have just chosen arbitrarily. We can say that if there are more particles within a specific distance, then your intensity becomes less or more or whatever we choose. We can do that. Absolutely.
Right. Or should we leave that as something that
we will upload this to GitHub and we'll allow you to play around with this one. So essentially what we are saying is that these particles that come together, they're not very stable. Yes. Not stable means they become so violent when they come and interact with each other.
Right.
You can make this stable by saying that take a particle, if within a specific radius, if there are more than let's say 5, you can reduce the intensity of this force.
Nice.
By the way, this is the one that defines how much force is there between. The bigger this number is, the more force there will be between the particles. So if I was to like sort of reduce this to let's say 2, you'll see a remarkable difference in how they.
Just less.
They're just lazy.
They
will come together. But
they are coming together.
They somehow make bigger particles.
Right?
They somehow make bigger particles, which is, I mean, okay. I'm not saying I'm not surprised by this, but this is a little bit surprising. That they form longer chains,
groups.
Wow.
So now it's more like the rules have become a little more clear.
Correct, as to what's happening.
Yellows are obviously attracting each other and they're staying like that. With the green, maybe
yellows and blues don't like each other. If you can see,
right, they're getting away.
They're getting away from each other.
The blue and green are very happy. They're sticking together.
Oh man, I like the fast movement, but I'm also liking what I'm seeing over here.
Correct.
Right. I mean, this gives you a little bit more time to observe what's happening between these particles. So shall we just leave it at this and upload it to GitHub as is?
Right.
And we'll sort of let the audience play with these variables.
Right.
Yeah. Oh, this is beautiful, man. Come on. Oh. Yeah. I mean, yellows obviously don't like others. They only like themselves.
They seem to be.
They seem to be clumping with each other. And yes. Wow.
Even the blues are see on the right, they're forming big
chains over here.
Chains. Very interesting.
Yes, it is. Okay. All right. I think that's about it for this week's episode. So all of this will make it available on GitHub and everything. Let me just switch cameras here. I think I have switched cameras. Yes, I have. Okay. So that's about it for this week's episode. A very beautiful particle system. If you like this content, leave a like. Share it with your friends. This code is available on GitHub. You can play around with it. Play around with a lot of the constants we have defined. The maximum speed. You can probably have like a minimum speed also if you want. But the framework is already available. And I think this can definitely benefit. I mean, right now it's all random.
Right.
But if you can actually define very specific rules between these particles,
correct.
I think it can definitely use that. It'll be great. Yes. Do subscribe to our channel if you like this, and leave a comment as to what you want to do, what you want us to do. I think next week, I want to do some sort of a very simple ripple system. Like take an image and have a ripple go through
effect.
that. So we'll a ripple effect go through it. So we'll look at that next week. A very simple rippling system.
Right.
Yes, that's about it. Thank you so much for joining.
Thanks.